Hi everyone. Yeah. Like I promised, let me talk about product of topological spaces and the, topology on the product space. So, to begin with, let me define, what do we mean by product of, in general sets. So, if you have, say, let X alpha be a collection of sets. Collection, note that this is a collection, not a set. Okay, like X alpha can be X beta for alpha different from beta. That's what I meant. So let this be a collection of sets. Then, so the notation for product is product. Like this, you write a small pi or capital pi. I think small. Whatever is this notation, product we call it X alpha, alpha here. So what is it, guys? This is just collection of all f from f is a map, is a function from your index set into union of x alpha, alpha in capital lambda, such that the conditions what you should have is, so f of alpha should lie inside x alpha for every alpha in capital lambda. That's what is the condition. So that is how we define, in general products. So if you take this capital lambda to be, say, natural numbers. So, and all x alphas say R. So like a particular example is, say, this is N and say x alpha is equals to R for every alpha in natural number. Okay. Yeah. You may write in place of alpha small n. That looks nice, right? So if you see what is the product in this case, this is nothing but collection of all sequences of real numbers, right? So this is an example. So like you write sequences in a very compact notation, like something like this, right? N in N. So similarly, any product space you can also write in the notation, that this notation. So how you can define it to be like this also. I'm defining now with black color the product. So this is actually also same as small x alpha. It's identification, meaning okay, I will tell you, such that x alpha is in capital X alpha for every alpha in this. So what I meant by it's in, what word I use? A different representation. I forgot the word. So, or the identification in the sense that if you take this set and if you take this set, there is a 1-1 onto map between them, right? This is an exercise, right? For you guys. So these two sets are equivalent. So like for example, if you call this capital A and this capital B, show that there exists a 1-1 onto map between A and B. So basically, any way you like. This is a more convenient way to write sometimes, and sometimes the above way is more convenient to write. Most of the circumstances which you will see, the B one, this one we use, but let me tell you, the first one is quite useful. I think you may see it in module theory or when you study something called compact open topology. So then that notation, that way of writing is actually useful. So okay, this is what we mean by product of sets. Now what we are interested in? We are interested in product of topological spaces. So let X alpha, tau alpha be a collection of topological spaces. Now, you are interested in capital X is equals to product X alpha. Definitely, you can give, you know, uncountably many or depending upon the cardinality of X alpha. So I will not use the word uncountably. I will use, you can give many topologies on capital X. But see, like in the subspace topology, there should be a good topology would be when there is relation between the topologies of X alpha and the new topology, what we want on capital X, the products. So those kind of topologies we are interested in. So we will study two topologies and then we will see like which one is better in some sense. Okay, so let me begin. So you may guess, you may guess, and it's indeed a good guess if you have guessed a topology that you just take product U alpha, alpha in this, okay, and say U alpha belong to tau alpha for every alpha in this capital lambda will give you a topology on capital X, right? That's the most natural way to think, right? If you have studied metric spaces before, then that's how, if you take two metric spaces and the product of those two metric spaces, that's how you, you may think, okay, this kind of open set should be there, right? These should be the open sets. Okay, for example, you may have that analogy in mind that A comma B, this is open in R, so this will implies A comma B cross some similar kind of interval. This this will be open in R square, right? That's what the natural guess is. But does this forms a topology? Meaning, does it satisfy this idea? Does it satisfies those three conditions? That's a question. So, I will give you a small homework. Try to show this is a topology. and observe the problem. So what I'm saying, this will not be a topology. So we need to somehow improve the definition, right? But one thing we want to keep in mind, this matrix based kind of result. If I have an open interval in R and I take two open intervals and take their product, then that will be open in R square, right? So this thing I want to retain in my definition, such kind of, because whenever you generalize something, you should not disturb whatever is happening in particular examples, right? Or in particular scenario. So what we want, we must have kind of sets. Okay, let me up this. Yeah. So we may want, because I don't want to disturb the idea, so we may want this kind of sets where u alpha is in tau alpha for every alpha to be open in topology or sum on X. We may want this, right? Like, like it is in R and R2. So something similar. But you will observe that this is not a topology. But there is a small homework for you guys. Show that script B is equals to, I'm defining the same collection. U alpha belong to tau alpha for every alpha in capital lambda is a basis for some topology on your product X, which we call box topology. Okay, so I hope you remember how to show this. First of all, for every point in X, you should have a member of this script B containing that point, right? Another thing is for any two such members and a point in it, you should have some third member containing that point and contained in intersection of those two sets, right? So it's not very difficult, okay? Just you have to follow the definitions carefully and you will be through. So I will skip this because we have already discussed some examples of bases and all. If I write everything also, that also is kind of spoon feeding, which I don't want to do. And this is, in almost every book, so you can read also on your own if you have some problem, or you can ask in comments. Okay. So the topology for which this collection is basis, we will call it box topology. Let me give you an exercise again, one more exercise. Let x is equals to r to the power n, so r cross r n times with the standard topology. What is the standard topology? By this Euclidean metric. So No, first show that above topology, the standard with the Euclidean metric, above topology is actually same as box topology, what you have defined above. Okay, basically you have to show the two topologies are same. If you divide if you define it in above fashion, or if you define like this. Okay, yeah. And another thing, this you might have done in calculus. What that say f from some, okay, not z. Let me take r only, or some, yeah. For example, r to rn is continuous if and only if, so this Pn, so F composed with Pn, this will be from, I will define what is Pn, R to R. So what I'm doing, Pn, I'm taking the projection on the, let me use rather than n, k, on the kth coordinate. So if I have this Rn to R, so what this Pk will do to some element xi, we'll just map it to 0, comma 0, 0, xk, 0. Okay, sorry. This will just map it to xk. So the kth projection, right? These maps, So yeah. So f is from R to R, Rn, and these are from Rn to R. So you have this f, you have this pk. This will be this composition pk composition f. This arrow means this composition hold. I mean, if you go here, and come here, these two functions are same. So we say diagram commutes. So we use this arrow. So the result is, so this is continuous if and only if these projection maps are continuous for every k in 1 to n. This you have shown in maybe your calculus course. So this is another exercise. If you know it, yeah, you can skip it. Now, don't you think when I'm defining a topology on product, so this is any product. I have taken just finitely many copies of R. It can be infinitely many copies of R, or it can be some very uncountable sets, right? Any product. Index set can be anything, right? So something like this we want, you know, to hold, right? This kind of property we want to hold. It's a beautiful property, right? Checking a map is continuous. You just on the product, like from some space to product, you know, uh, you compose it with projections, and if those are continuous, that kind of simplify our work, right? So we definitely want to see, does we have this property? What I mean, so say f from z is some other topological space to product f alpha is continuous. This is the one statement. Second, P alpha composed with F. What will be? This will be from Z to X alpha is continuous for every alpha in where capital lambda. So, is this true that these statements are equivalent? Are above statements equivalent? That's the question. Okay. So, let's see. Are these? So, you have given. So, okay, let me answer this. So, actually, the amazing thing is the answer is no. And it's a very big demerit because from some space to the product, if it is there and if something is true on components, we always want it to be true for the function also, right? The same property like in differentiability or say continuity. So that's why I said this is a kind of disadvantage. So why this is not true? Let us see. First of all, observe that if you take these maps P alpha from product X alpha to X alpha. See, if you want, you can change this alpha index. This alpha is varying here arbitrary and this is the fixed one. So if you want, you can change it like this, say beta is continuous. And what topology we are taking here? Box topology. So let us see that these maps are continuous. So how to show some map is continuous? You have an open set in codomain, you pull back it and see if it is open or not, right? So let U alpha be open in beta. So guys, what is P inverse of U beta? This you can check. This will be product V alpha in capital lambda where V alpha is equals to X alpha for every alpha not equal to beta, right? Projection you are taking. So all other sets you take any point, it doesn't matter, right? And this V beta is actually your U beta, right? That's what the description is. You can visualize it from, you can take a map from R cross R to R, like f of x comma y is x. So try to pull back any set there. So it doesn't matter what is y component. That's why that whole R will come. So similar to that. Or you can show this also. How you show two sets are same? You have to take a point in one, show it is in another, and vice versa. So you can show that also. That I'm leaving out. Many exercises we will be like small exercises we will be leaving. And note that this is open where? This is open in. This is open in where? This is open in this product X alpha. By definition, in fact, it's a basic open set, right? Because it belongs to basis. So basic open. So you see, it's easy to see that P beta is continuous for every beta. Now, so See, one thing is very clear. What? 1 implies 2, right? Why? Composition of two continuous map is continuous. So this is another exercise for you guys. What? That composition of two continuous map is continuous between topological spaces. You can prove it just by definition. Okay. Okay. Now, let us see why the converse is not true. So it's a beautiful example. So let f from R to R omega. So what is R omega? R omega meaning R cross R cross R countably many times. So what we are doing is, and this of course with box topology, and define it to be f of t goes to t comma t comma t like this. Okay, now note that product minus 1 upon n, 1 upon n in n is open in R omega. This is by definition. In fact, it is again a basic open set, right? Because open interval minus 1 to 1 upon n is open in R. Okay. Now, let us see what is, let's call this say V. What is F inverse of V? Shall I give you another exercise? Show that F inverse of V is, okay, just a second. Yeah, is singleton 0, which is not open, right? Where? In R. So this implies F is not continuous. But if you take any projection on any nth level and you compose it with F, this will be a map from R to R, and this is nothing but your identity map, right? You can check it. So this is continuous for every n in n. So you see, this is a counter example for 2 implies 1. So 2 doesn't implies 1 in general. There might be situations where it implies. Okay, we will see one such later on as an exercise problem. But this doesn't happen here. So the thing is, now we will be interested in, some topology where this equivalence happens of 1 and 2. So let me define that topology. And that topology we will call as product topology or Tikhonov topology. So product topology Tikhonov topology. So this will be a topology. It's the name is credited to Tikhonov. He was a mathematician. He was a topologist, and you will see a very famous theorem of him, like maybe after many lectures. Yeah. So let us define this topology. So there are two ways. One is we construct a topology from subbases. So from subbases, you can go to bases and then you get a topology. Or directly give the bases. So we will follow the subbases one. Okay. So recall X is product of this, and these are topological spaces. Collection of topological spaces. That's what we have. Now, and say these are your projection maps. Okay. Define a collection S. So how we are defining it? P alpha inverse. So meaning projection on alpha coordinate of U alpha. What is U alpha? So U alpha is open in X alpha or belongs to tau alpha, and this alpha varies. So the index set for S is index set is the open sets in all, first of all, these alphas and the open sets in X alphas. So that is what the index set is, the cross product of those things. Okay. So this kind of, and you have seen what is this, guys? This is product, some V beta. Always better to change the index while defining. So when V beta, V alpha, alpha is equals to U alpha and V beta is equals to X beta for every alpha, yeah, beta not equal to beta not equal to alpha, right? This we have seen. Now, you can prove this as a subbasis, right? Show that S is a subbasis for some topology on X, which we call product topology. Okay, is it fine? Oh, I wanted to define this topology in some other fashion. It's okay. We will do it as an exercise. Okay, now tell me. So this is the subbasis, and yeah. So what would be the basis? If you remember the lecture, the basis corresponding to that subbasis will be show that corresponding to that subbasis. So I'm writing B suffixes. So what I meant, the basis corresponding to that subbasis will be of this form. So product of U alpha, alpha in capital lambda such that U alpha is equals to X alpha for all but finitely many alphas. Meaning you leave finitely many. Apart from that, all are the whole spaces, X alphas. Okay. So how this is coming? Basically, you can show this. Say, okay. So to like, okay, let me just. I will not prove it. You can prove it. So if you take some P inverse of say beta I, some indices, U beta I, so this and intersection of them, 1, 2. So because from a subbasis, you get a basis by doing finite intersections of subbasic sets. Say some K. Show that this will be of above form. So like this. Okay, that's all you have to show. So you have to properly do the intersection, and you will be able to do because you have already seen how the intersection will look like for these kind of products if you will prove this exercise where I have given show that basis for box topology. Yeah, this red color one. So yeah, I know this is like lot of exercises, but yeah, you have to do this. You have to dirty your hands. That's how you learn mathematics. Okay, now I will give another exercise. So theorem. So the problem will be sorted now. What problem? So let Z and X alphas, alpha in some capital lambda, be topological spaces. Then F from Z to product X alpha with product topology. Okay. By the way, later on, whenever there is no mention of any topology, we will always take product topology is continuous if and only if, what is the statement? If you compose these maps, so that will be from Z to X alpha is continuous. So before that, I think I have mentioned the exercise. This you can directly use this exercise. What? So okay, let me write it as a hint. F is okay. F from X to Y is continuous if and only if inverse image of every subbasic open set is open. I may have mentioned this exercise before. If I have it, then you can also show this. This is just by definition. Okay. So this will help you to prove this result, more easily because topology is huge, basis is somewhat less, subbasis is somewhat more less, right? Okay. Is it clear? So this property is very important, and this we will get if I take rather than box topology, I take product topology. I want to give you, this is also exercise. Whatever the spelling is, sorry for the spelling mistake. I want to give you one more problem. If capital lambda is a finite set, show that box topology coincides with product topology. So that's why in calculus, when you have defined open sets in Rn, you just take like product and you do everything with them and you say, haha, that is sufficient. So when I have a finite product, these two topologies are actually same. This is very easy to prove it. Just use basis of both. I should write E rather than I because yeah, I'm using it as plural. Both topologies. So you see that's what the relation is. And definitely you have an example when the product is not finite, these topologies are not same. What is the example? This R cross countably many times. So if you take the product topology by above result, you know, uh, any map from that space to that space, something like that, those properties will hold. But if you take box topology, that's not the case. Another thing you might have observed that in general is also an exercise. What is the relation between box topology and product topology? In general, product topology, does it have more open sets or less open sets? That's what. Think for a moment. So, product topology is coarser than, means smaller than, contained in box topology. These things are, by definition, everything. That's why I'm leaving them as exercise. So let me do one very, beautiful result and I will probably prove it fully in full details. So theorem, equivalent or slash categorical. Okay, let's not go into categories. So equivalent definition of product topology. Topology. So this is very, very, very useful at many places. You will realize when you go deep down in mathematics, like, okay, so what is the equivalent definition is? So the product topology on, of course, the product is the smallest topology such that something striking in your head in the last thing, in the last, uh, video, we have seen that subspace topology is the smallest topology such that inclusion map is continuous. So something similar. Smallest topology such that what are the maps here? The natural maps are projection maps, right? Such that P beta from x to x beta is continuous for all beta. I have given you some exercises also like long time back, when I was discussing continuity. So I have uploaded. Okay. So let me have as a remark, refer and compare above what we have done above this topology, product topology, and this result with the with exercises given in, let me see which lecture. So just a minute. Okay, to open YouTube. Just bear me for a moment. With me for a moment. Yeah. So I think it's the lecture number 15. Yeah. So in this topology 15, and the title was Continuous Maps Between Topological Spaces. Part 1. So you might be wondering when the part 2 will come. I have started with, something else. Don't worry, my next video will be on part 2. So, but compare with above with the exercises given in at end of video. What is the spelling of video? That's yeah, very difficult for me sometimes. VIDEO or VEDIO, please, or maybe VEDIO. Please, you know it. I don't know. So yeah. So compare this thing with that. So you will also get the directly idea. Oh yeah, how the topology we have constructed above is the most natural way to define the smallest topology such that all of these maps will be continuous. So please refer to that section. So yeah, let me prove this because I have told you that yeah, I will prove it. So prove. So say let tau prime be any other topology, means other than product, other topology on X such that P beta from X tau prime to X beta is continuous for every beta in capital lambda. And let us give some symbol to the product topology also corresponding to that subbasis. So let us call like this. Let denotes the product topology. So what you have to show, guys, you have to show that this product topology is the smallest such that this above thing happened, right? So we have shown already that the product maps. Have we shown? No, we haven't shown. So, okay. So to show, number one, tau script s is contained in tau prime. Number two, it's like subspace only. Everything is like that. This P beta from x tau s to x beta tau beta is continuous for every beta n. So 2 is exercise, huh? This you can do because we have already done something similar in box topology also. So it will follow like that only. Okay. Let's observe why first is true. It's like subspace topology only. There's the scenario is different. So okay. So let U contained in, or say let's use some different notation. V, let V belongs to tau suffix s. What we have to show? To show V belongs to tau prime, right? That's what we have to show. So, if V belongs to tau s, okay. So it is sufficient to show, that every basic open set with respect to tau s sits inside tau prime, right? Because if basic open sets are there, then every open set will be there, right? Because tau prime is a topology. We have used this idea also before. So without loss of generality, assume V is a basic open set. So it has this form. Say V alpha, where V alpha open in, where X alpha and V alpha, say this is equal to the whole spaces for all but finitely many, right? So let's say V alpha is equals to X alpha for all alpha not equal to alpha suffix 1, alpha suffix 2 and alpha suffix k. And V alpha is equals to V alpha is X, is not equal to, so it is properly contained. V alpha is strictly inside X alpha for every alpha equal to alpha 1 to alpha k. So that's how is this description is, right? We have to show that this V is also in tau prime, right? Now, note that for I equal to 1 to k, V alpha is open in where? X alpha, right? And this map P alpha from X to X with the topology tau prime to X alpha, there the topology is fixed, right? It's continuous, right? Now, since this is continuous, so pullback of V alpha means inverse image will be also continuous. Open in X. So P alpha I inverse of V alpha I belongs to where guys? Tau prime. For every I in 1 to k. Now tau prime is a topology. So since this is a topology, this will imply intersection of E alpha I, V alpha I is from 1 to k belongs to tau prime. And you can see this is exactly your set V by definition. This we have used this kind of equality I mentioned above and asked you to prove it. Right? So this is what we have shown. V was in tau s and now where is V? Tau prime. So this implies tau s sits inside tau prime. So tau s is indeed the smallest topology which makes all of these projection maps continuous. Smallest topology on the product which makes all of the projection maps continuous. That is what your product topology is. I think I should end this section and just let me tell you what we are going to do in next session. So we will see what do we mean by homeomorphism. I know I have defined it, but not properly. Homeomorphism. We will see example, properties of continuous maps. So I think I should end this session now. It's already a little bit long. So what we have learned today, let me just sort of, recap. So how to give topology on product, right? Okay, wait, I will write it. So what we have learned is number one, there are two topologies, box topology. Another is product topology. This has a demerit, you know what I'm talking about, which is sorted by this product topology. And C, note that product topology also gives us a class of continuous functions, right? So, in fact, this is also, I'm giving you more and more examples in abstract way for continuous functions. What are these? Projection maps. So you may say, Are projection maps will be always continuous, na? What is there? So my answer is no. If you take some other topology, it might not be. So if you take, say, this with again this topology in discrete, say just from R cross R, okay. And here you take real line R. So then P is not continuous. You can see this, why this is not continuous. Okay, fine. So you see, similar like subspace topology somewhat. So on these similar lines, we will discuss another topology also, but not now. So let me not disclose it. So these are the very, very important things and basic foundation for doing, topology in later on. And yeah, these concepts should be very, very, very clear. I can give you many more exercises, but yeah, let me stop now. Okay, thank you so much for your attention. And if you like the video, please, like it, spread it, subscribe the channel. Thanks a lot.